as I mentioned, the way this textbook is arranged is we introduce the fields, the field quantity in free space, where things are more simplified, and then we understand how matter, having material, is going to affect the field. So for the second PowerPoint set, I am going to talk about, don't like to have this guy here, let's drag it, right? So electrostatics in materials. So before we really go on, we have to understand how materials are classified. Okay. Right. I'm sure all of you have basic knowledge to how materials are classified. You can classify materials due to their density, right? Gas, solid, and liquid. But in electromagnetics, we classify materials based on their ability to conduct electricity. What does that mean? Well, we know materials are comprised of a lot of atoms, and atoms have electrons, protons, and neutrons, right? So somehow, if I can have a material and I add potential difference, and then I can have conducting current, that means I have a lot of electrons inside this material which can move. Okay? So for those material, we call them conductors. Metals are likely good conductors, right? So the materials that can conduct current are called conductors. On the other hand, if you have materials, even though you apply very high potential difference, you still don't have currents. And those are called insulators. They don't conduct current. And the reason is the conduction band where you have free electrons are very far distanced in energy from the valence band. Okay, so you don't really have a lot of electrons in the conduction band for insulators, right? And of course, you have material lying somewhere in the middle where you add, without applied potential difference, it does not conduct current. But when you apply above certain voltage difference, it starts to conduct current. So those are called semiconductors, like silicon, gallium arsenide. So these are all semiconductors. So in this class, I am not going to cover semiconductor. It is a course on its own. I am going to first describe conductor, metal, and then I'm going to talk about insulators. Alright, so metals first, and then insulators. I know some of you are falling asleep, so I want to probably wake you up. So what I plan to do, at least for today, I'm going to talk about static E fields in conductors. And on Wednesday, we can talk about the static E fields in insulators. Insulators are also called dielectrics, 介电载质, dielectrics. So for these two, I'm going to leave until maybe next week. Alright, so we are going to talk about static electric fields in metallic materials, conductors. When you think of conductors, what does the name imply? And actually, I talked about it. If you have a conductor, conducting material means you have a lot of free electrons. So if you apply certain potential difference, you have electric current flowing across the material. So what happens when you have this big battery, which provides a huge potential difference. But then you have a wet chicken. The chicken gets electrified, right? Because chicken is wet, water, you have a lot of water, you become conductive. Don't do this at home, okay? Please don't do it. So why do I choose a wet chicken? Because we are in the department of electrical engineering. So if you understand about Chinese, electrical engineering transferred into Chinese, the pronunciation is exactly an electrified chicken. 电机, right? Okay. So be careful when you study in our department, right? Okay. So if I have a piece of good metal, it's a very good conductor, right? There are two basic aspects to a very good conductor. In the future, I'll just call it perfect conductor. If you have a perfect metal, perfect conductor, you have two special aspects. One is inside this metal, you are not allowed to have charge distribution. So this charge density inside the metal has to be 0. That's point 1. Point number 2, inside the metal, you cannot have electric field. Right? So some of the students are extremely naughty. You might be wondering, oh, what happens if I inject charges into the perfect metal? What is going to happen? I can tell you the answer right now, but later on, I will prove it to you. Right? If you have a perfect metal to start with, but you're a naughty student and you purposely inject a lot of free charges into the metal, you want to challenge the fact that the professor told you there cannot be charge inside the metal, so you purposely inject those charges into the metal. What I can tell you is, within a split of a second, much shorter within the blink of your eyes, roughly 10 to the minus 19 second. That means zeptoseconds, 100 zeptoseconds. All the charges will be forced to surface. What does that mean? Even though you inject a lot of charges into the metal, almost instantaneously, all the charges will be forced to swim to the surface of the metal. So that inside the metal, you still don't have charge density. And if you don't have charge density, by Gauss's law, you cannot have electric field intensity distribution. Okay? Later on, I will prove it to you. I can even just show you the time scale. It's really zeptosecond. But up to now, the basic two assumptions for perfect matter are: you cannot have charge inside the metal, you cannot have the field inside the metal. You must be scratching your head, why not? Why not? why do the charges need to be distributed along the surface but not inside? Well, let me ask you in a very philosophical way. If you have a piece of conductor, a very good conductor, a perfect conductor, what do you think of its potential? You have a piece of perfect conductor. It means, well, the electric potential should be the same everywhere, right? If you have like gold or silver, platinum, you have this solid gold, and you ask yourself the potential at this point, potential at this point, potential at this point, aren't they supposed to be the same? Right? So let me just draw a simple circuit diagram for you. This is something you learned, right? You have a resistor, you have a capacitor, you have an inductor, L, C, R, right? They are somehow connected together at 2 points. So these are conductors, right? Resistors, capacitors, inductors are somehow manufactured, so you have 2 conductors at 2 ends, and you're free to connect them. So if you tell me this point, V1, V2, V3, they are somehow linked together through good or perfect conductors, V1 and V2 and V3 can only be related in one way. They're all equal, right? Because they are the same node. So they can only have one electric potential. That's called voltage. So this is based on our understanding. If you have perfect metal, so inside the metal or everywhere on the metal, if it's coming from the same piece, you have the same potential everywhere. Okay? So if any 2 positions are having the same potential, it also implies inside the metal you cannot have field distribution. Why? Can anyone answer this question? It's too bad you're not in classroom. Usually I like to ask a lot of questions. The answer lies directly from our previously covered topic, electric potential. Right? Electric potential, the potential difference between 2 points, is P1 and P2, can be derived when you perform the line integration in some kind of field distribution. But now the fact that this has to be 0 everywhere within a perfect metal or conductor, it also implies within the metal you are not allowed to have E fields. Okay? Perfect conductors have the same potential everywhere. So inside the metal, you don't have E field distribution. Once you do, if you do have E field distribution, it means within the metal, point by point, you might have potential difference. But that really contradicts our understanding. right? So this comes actually first. Inside a good metal, you cannot have a loud field. And then you use Gauss's law. If you cannot have fields, you cannot have charge distribution. All right. So this is the sequential. Based on our understanding, we don't have potential difference. Then we don't have fields. We don't have charges. Okay. So that's exactly what Gauss taught us. So inside, if you don't have field, you don't have charge. Right? So now take a close look. We can try to understand this in a more detailed way. If within the metal, I have 2 points, and somehow they don't have the same potential. If they don't have the same potential, that means I have E-field distribution. Okay? If I have E-field distribution, I have potential difference. What is going to happen for conductors? Conductors have lots and lots of free electrons. Right? Free electrons mean they're free to move around. So once you have a field distribution, that charge, that free electron, is going to move. Right? So if you have high potential, low potential, your electron is going to move. Okay? And that really violates our basic assumption of static E field. Right? Okay, so in a static condition, let's summarize again. Inside the metal, no charge, no field. But the charges are allowed to locate on the surface of the metal. Right? Now, take this challenge. Please draw out the resulting electric field lines due to the surface charges. Try to draw out the resulting E field lines. How difficult can that be? Right? You have a metallic surface, you have a charge, right? I still remember the professor taught me, well, if you have a charge, the E field lines are just radiant. Right? It goes out, it goes out, it goes out, like that. How difficult can that be? Well, then you're totally wrong. As I mentioned, if you have a single charge, yes, you will have a radiant E field line. But as we just talked about, when you have two charges, the field lines are dramatically different in geometry. And now you place a charge on top of a perfect metal. That fact is going to change your field distribution dramatically. Right? So think about it. Let's take a close look at only two field lines. This one and this one. Let's forget about all the other field lines. So I have a perfect metal here. I have a single charge here. Let's take a look at the two extreme cases where one of the field line is perpendicular to the metallic surface. The other one is tangent. Okay, so let me just write it. E tangent for this guy, and E normal for this guy. Which one of the two field lines cannot be there? You can only have one. This is tricky. What? You can only have the normal component or the tangential component. If you were forced to choose one, which one would you choose to survive? Any feedback from the students? No? Anyone watching? 19, yes, okay. Think about it. Okay. If you have tangential field line, what does that mean? As we introduced in the previous class, if you have a charge, a positive charge, and you're walking in the direction along the field line, you lose potential, right? So if you have tangential field lines, it means this point is having a higher potential as compared to this point. But they are all on the metallic surface. And that really contradicts to our understanding of perfect conductor. Because we said repeatedly, on any point within the metal, they have the same potential. Right? So you are not allowed to have the tangential E field lines. If you have them, you're slapping your face. If you have tangential component, that means, let me just draw this one for you, okay? For example, you have a flat metallic surface, and you have a charge. And you want to argue, yeah, I want to have the tangential field line. Then you're saying V1 and V2 are actually different. So that is not allowed. So for perfect metals, if you have the surface geometry, you know the geometry of your metal, and somehow you have charges, right, spread out on the surface. The only way you can have E field lines is they all point in the direction perpendicular to the local surface. In other words, all the field directions are parallel to the surface normal. Okay? So only the normal components are allowed. You cannot have the tangential component. Tangential means if you walk along it, you have potential difference. But potential difference appears on the same matter. But if you walk in the direction normal to it, that's fine. You're moving away from the matter. Okay? So I'm introducing this in a more philosophical way. I haven't invoked any math, but I'm just only describing what we understand about conductors. Conductors have equal potential, therefore they cannot have fields inside, they cannot have charge inside, they cannot have tangential field distributions. Even at the surface, it's not allowed. Okay? So, this is coming from curl of E is equal to 0. Right? The integration form is if you have a closed loop integration of E, it's 0 everywhere, right? If you have a closed loop. So now what happens if you have a conductor and you have another material forming an interface? Conductor, air, you have an interface. So this is to further corroborate you cannot have the tangential field component even though you have a point charge. Whenever you have the curl operation, you need to form a closed loop, right? So for this case, this true length can be, this delta H can be extremely short, so you don't really need to evaluate its contribution. You only need to evaluate the top segment and the bottom segment, right? So you only have to calculate the line integration of the E field inside the metal along this path C to D, and the E field contribution along A, B segment in air. But as we talked about, fields inside the metal is 0 everywhere. So here, you don't have any contribution here. Therefore, you cannot have any contribution from AB. That is telling you, that's confirming, even though you have a charge position at the interface slightly in the air side, you cannot have the tangential component. Because by default, curl of E is equal to 0. So at this interface, no field inside. Inside the metal, there's absolutely no field. So no tangential field. If you don't have contribution from this segment, you cannot have contribution from this segment. Right? On the other hand, Gauss's law tells us divergence of E is equal to rho divided by epsilon 0. So eventually, yes. If you have a piece of conductor and you have the air, so it forms an interface, at the interface you can have charges deposited along the surface, and you can have all the field line emitted perpendicular to the interface. Once you know the charge density on the surface of your metal conductor, you know your field strength are all in a normal direction, and its quantity is your charge density divided by epsilon 0. Think about it. What is the difference in this case as compared to our uniform charge plane distribution? This is something we covered, right? If we only had a plane of charge, but it's not a conductor, then you are allowed to have normal E field lines pointing out. Above it, you have fields going up. Below it, you have fields going down. So if you only have a plane of charge distribution, you can have fields up and down, and therefore the magnitude is twice weaker. But in this case, you have perfect conductor, no field can be present within the conductor, but you have charges. So you can only emit the field outward and not into the conductor. Therefore, its strength is twice stronger as compared to a planar charge distribution. Right? So think about it. is quite unique. Perfect metals are really, really unique. Okay, so I'm adopting a very descriptive method to introduce perfect metals, but somehow I'm linking to the fundamental postulates, right? Curl of E equals to 0, divergence of E is equal to rho divided by epsilon 0. Right? So for that, let me conclude for the day.